Meet 11-year-old Zach and his 8-year-old brother Peter. These typically developing boys are here with their mom at the University of California at San Diego. The boys are participating in research that helps scientists to better understand the relationship between cognitive behavior and the developing brain. Each boy will have a brain scan under the watchful eye of developmental cognitive neuroscientist Joan Stiles. This scan is called magnetic resonance imaging, or MRI. It's non-invasive, produces no radiation, and is a safe way to see what's going on inside the brain while the child is engaged in a task.
Okay, one more of those 1-minute scans. Nothing for you to do.
Stiles is interested in visual spatial processing, how we come to understand our visual world. So the tasks include looking at various shapes and patterns.
And while they perform a task, we very, very quickly and in succession take images of their brain, take pictures of their brain. We can then process those images in such a way that we can determine what areas of the brain have been active while the child was doing the task, and what areas of the brain were not active. Essentially, what this methodology has allowed us to do is to ask questions about how brain activation changes over time with development.
One question asked is how brain activity in children differs from that seen in adults. A second is how the brain processes whole patterns, like this Greek letter pi, and how it processes the parts, like the triangles. But importantly, Stiles' work also links brain activity to real-world behavior.
Okay, Zach, I want you to look at this very carefully and remember it because I'm going to take it away. I want you to draw it after I take it away.
Zach is able to quickly and accurately reproduce the whole pi pattern and its parts. How does the ability to reproduce complex configurations change with development? 8-year-old Peter does pretty well with the overall pattern, but like others his age, he has a harder time with the parts. Here are the two boys' drawings.
By the time children are about 12 years of age, their ability to process parts and process wholes of a pattern has reached more or less adult-like levels.
And here's how Stiles links these behavioral differences to brain activity.
When the children are in the scanner, sometimes we ask them to pay attention to the whole form, and other times we ask them to pay attention to just the small parts.
When older children are given this task, their brain activity resembles that of an adult.
Specifically, when adults are asked to process the whole pattern, a region in the right hemisphere activates, and when they're asked to process only the parts, a region in the left hemisphere activates. So you see a specialization of function.
But in younger children, there's no such specialization.
First, there's more activation overall in the brains of younger children when they're doing either the whole pattern processing or attending to the parts. Furthermore, when we look at their processing of parts, we see that activation is much greater and involves both hemispheres of the brain, suggesting that the task might be harder for the children and they're engaging all of their visual pattern processing resources to perform the task.
Newer technology has enabled researchers to link brain activity and behavior. There are also medical applications of Stiles' work. She studies a population of children who've had strokes, either before or right after birth.
What we can see is the large area of damage in the left hemisphere.
Here are some drawings done by stroke victims at age 5. They've copied that same pi pattern we've seen before. But in those with damage to the right hemisphere, there's trouble copying the whole pattern. But damage to the left hemisphere results in difficulty copying the parts. However, by age 8, something amazing happens. The drawings improve dramatically. They look much like those of typically developing 8-year-olds, and that raises a question.
If the child has had an injury to that region of the brain and it's not there anymore, how does the child carry out that processing?
The answer lies in brain plasticity. Somehow the healthy hemisphere takes over.
And the MRI scan shows us how children compensate at the neural level. In children with left-sided injury, we see activation in the uninjured right hemisphere for both the whole pattern and for the parts processing. In the child with right-sided injury, we see activation in the left hemisphere for both the whole pattern and for the parts.
But Stiles emphasizes that plasticity does not just apply to injured brains. It's a normal mechanism that allows all of us to adapt.
The operation of plasticity may be more obvious in the child who's had a stroke, a child who must compensate for substantial loss of neural tissue. But we think that plasticity is a normal part of brain development and part of how brains become shaped and wired across development.